Good day, students. I'm Lloyd, your AI narrator of this subject, aircraft welding AMT 116. This is a short video that covers the prelim topic, so please take note of some important details or have a copy because, after this short slide, there are questions to answer. Serve as your attendance. Please be advised that before the semester end, you will perform one of the types of welding, namely shielded metal arc welding or stick welding at Flight Dynamics School of Aeronautics. Don't worry, your laboratory instructor will guide you and help you on how to operate and weld. This course deals on the fundamental processes in welding, equipment's familiarization in welding, identification of metals to be welded, standard procedures in welding application, proper use of oxyacetylene equipment and gas welding techniques. Also included are the basic application and welding processes of electric arc welding. As the technology and manufacturing processes evolved in the aircraft and aerospace industry, lighter metals such as aluminum, magnesium, and titanium were used in their construction. New processes and methods of welding these metals were developed. This chapter provides some of the basic information needed to understand and initiate the various welding methods and processes. Welding is a process that joins metal by melting or hammering the work pieces until they are united together. One of the most practical of the many metal joining processes available that offers rigidity, simplicity, low weight and high strength. With the right equipment and instruction, almost anyone with some basic mechanical skill, dexterity, and practice can learn to weld. There are three general types of welding. Namely, gas welding, electric arc welding, and electric resistance welding. Each type of welding has several variations, some of which are used in the construction of aircraft. Additionally, there are some new welding processes that have been developed in recent years that are highlighted for the purpose of information. Gas welding. Gas welding is accomplished by heating the ends or edges of metal parts to a molten state with a high temperature flame. Gas welding was the method most commonly used in production on aircraft materials under 3/16 inch in thickness until the mid-1950s, when it was replaced by electric welding for economic reasons, not engineering. Gas welding continues to be a very popular and proven method for repair operations. Under gas welding is oxyacetylene welding. Oxyacetylene welding, also known as oxy-fuel welding or acetylene welding, is a process that uses oxygen and fuel gases to weld and cut steel or metallic components with a temperature of approximately 6,300 degrees Fahrenheit, is produced with a torch burning acetylene and mixing it with pure oxygen. Hydrogen may be used in place of acetylene for aluminum welding, but the heat output is reduced to about 4,800 degrees Fahrenheit. Nearly all gas welding in aircraft fabrication is performed with oxyacetylene welding equipment consisting of two cylinders, acetylene and oxygen, acetylene and oxygen pressure regulators and cylinder pressure gauges, two lengths of colored hose, red for acetylene, and green for oxygen, with check valves and adapter connections for the regulators and torch. A welding torch with an internal mixing head, various size tips, and hose connections. Welding goggles fitted with appropriate colored lenses. A flint or spark lighter. Special wrench for acetylene tank valve if needed. An appropriately rated fire extinguisher. On the next video, Mr. M. Tutor will discuss the equipment setup in gas welding. Let's just pretend that the blue hose is green.
Equipment setup in gas welding. At the end of this topic, you will be able to describe the equipment setup in gas welding, demonstrate the equipment setup for oxyacetylene gas welding. Gas welding is a welding process that melts and joins metals by heating them with a flame caused by a reaction between the fuel gas and oxygen. Due to high flame temperature, the oxyacetylene welding is mostly used in industries. The equipment involved in gas welding are cylinders, oxygen cylinder, acetylene cylinder, regulators, welding hoses, check valves, flashback arresters, and torches. Before learning about the welding process, we will first set up all these required equipment at proper places. Now, we will see the functions of these equipment. Cylinders. Oxygen and acetylene are stored in steel cylinders that can withstand extreme high pressure. Cylinders should always be secured and transported in the upright position. When a cylinder is not in use, close the valve by steel cap. Cylinders should be checked regularly with the date of the last test stamped on the top of the cylinder. Oxygen cylinder. These cylinders are painted in black color, filled with oxygen. The size of the cylinder ranges from 20 to 300 cubic feet, which contains compressed oxygen at high pressure of 2,200 pound per square inch. Acetylene cylinder is painted in maroon color. The size ranges of this cylinder is from 10 to 400 cubic feet capacity. Acetylene is dissolved in acetone, which is stored at a pressure of 250 pounds per square inch. Regulators. The primary function of these regulators is to control the gas pressure during welding. It reduces the high pressure of the gas stored in the cylinder to the working pressure of the torch. Welding hoses. The cylinder regulators and torch are connected together by welding hoses. These hoses should be color-coded. Blue color hoses for oxygen and red color hoses for acetylene. The oxygen hose is fitted in right-hand threads, whereas acetylene hose is fitted in left-hand threads. Check valves. It is installed between the hoses and torch. These valves are designed to permit the flow of gas in one direction. The purpose of this valve is to prevent the reverse or backflow of the gas with minimal leakage. Flashback arresters. It is used to stop the flame or reverse the flow of gas back up into equipment or supply line. Flashback arresters must be fitted on both oxygen and acetylene regulators. Torches. It consists of handle, oxygen and acetylene valves and mixing chamber. The oxygen and fuel gas flow through the tube and are mixed in the mixing chamber. Then, the mixed gases get ignited at the tip of the torch. Suitable tip is placed at the end of the torch, which increases or decreases the width of the flame. Equipment setup for oxyacetylene gas welding. Take all the equipment such as oxygen and acetylene cylinder, hoses, regulators, check valves, flashback arresters, and torch. First, check whether the oxygen and the acetylene gas cylinders valves are turned off. The two cylinders are secured in an upright position and placed on a wheeled trolley. Connect the regulators to cylinders for which they were designed. Connect oxygen regulators to oxygen cylinders and acetylene regulators to acetylene cylinders. Note, the pressure value of each cylinder should be 0. Next, fix the flashback arresters to both oxygen and acetylene regulators. Attach the hoses to the flashback arresters. Never use an acetylene hose on an oxygen cylinder or an oxygen hose on an acetylene cylinder. As a further safety precaution, connect the oxygen hose in right-hand thread and acetylene hose in left-hand thread. Connect the check valves at the bottom of the torch. Finally, install the torch to the end of the oxygen hose and acetylene hose. Select the suitable tip for the task and screw it at the end of the torch. Hold the torch handle in your hand and adjust the oxygen and acetylene taps. Position the tip away from your faces. Now, you are ready to use the torch. Half turn the main valve on the top of each cylinder in counterclockwise direction. Turn the regulator valve and set the pressure for each cylinder. This is your working pressure for welding. Before you light the torch, check your working area. Make sure there is no flammable material or fluids nearby, and also clear the workmates from the area. Now, ignite the torch. Slightly turn on the acetylene valve. That creates a flame at the tip of the torch. Then slowly open the oxygen valve on the torch handle. As you open the oxygen valve, you will see the color of flame changing. The pure acetylene flame is yellow, and if you add oxygen, it changes to blue. Now, you can adjust to the desired flame width for the welding you are doing. Summary. In this topic, you have learnt that the equipment setup in oxyacetylene gas welding are cylinders, oxygen cylinder, acetylene cylinder, regulators, welding hoses, check valves, flashback arresters, and torches.
Electric arc welding. Electric arc welding is used extensively by the aircraft industry in both the manufacture and repair of aircraft. It can be used satisfactorily to join all weldable metals, provided that the proper processes and materials are used. There are 4 types of electric arc welding in aircraft industry. Shielded metal arc welding or stick welding, SMA. Gas metal arc welding, GMA. Gas tungsten arc welding, GTA. Plasma arc welding, PA. In shielded metal arc welding. This is the most common type of welding and is usually referred to as stick welding. The equipment consists of a metal wire rod coated with a welding flux that is clamped in an electrode holder that is connected by a heavy electrical cable to a low voltage and high current in either alternating current, AC, or direct current, DC, depending on the type of welding being done. A short video that help you easily understand shielded arc welding.
What is stick welding? Stick welding is an electric arc welding process that uses rod-shaped metal electrodes that are covered with a flux material. The American Welding Society calls this process shielded metal arc welding, or SMAW. You may also hear this process called manual metal arc welding, or MMA welding. Some people refer to this process simply as arc welding, but shielded metal arc welding, or stick welding, is just one of many types of arc welding. In stick welding, an electric current flows through a metal electrode or stick. An arc forms between the end of this electrode and the workpiece. The arc melts both the metal in the rod and the metal in the pieces to be joined. The metal from the electrode is ejected into a molten weld pool and mixes or coalesces with the workpiece. The metal in the workpiece is called the base metal, and the metal added to the joint from the electrode is called filler metal. Stick welding always adds filler metal to the joint. Because the electrode is constantly melting away and becoming part of the welded structure, stick welding is known as a consumable electrode process. As the electrode is heated by the arc, some of the covering of the electrode releases protective gases that shield the weld and help stabilize the arc. The remaining covering melts and covers the molten weld pool with a protective slag layer. This slag layer protects and helps shape the weld as it solidifies, but it must be removed when the weld is cool. Since the gases generated by the flux covering are able to completely protect the molten weld, there is no need for other shielding equipment such as high-pressure gas cylinders, regulators, or hoses. Compared to other welding processes, stick welding equipment is often very simple. Sometimes the only controls on the machine are current and polarity. Many important welding variables come from how the person doing the welding positions and moves the electrode. For this reason, the quality of welds produced by this process depends greatly on operator skill. In stick welding, 2 insulated wires are connected to the welding machine. One lead goes to a clamp, which is connected to the work. This is called the work lead. The other wire goes to an electrode holder. The uncovered or grip end of the electrode is placed into the electrode holder. The polarity of the welding setup refers to how the electricity flows from the machine to the workpiece and back. The current will either be AC or DC. In AC, or alternating current, the direction of the flow of the electricity changes directions many times every second. Direct current, or DC, is like the flow of electricity from a car battery. One lead is always positive and the other is always negative. DC can be set up 2 ways in stick welding. One way to connect DC is DCEN, or DC electrode negative, which is often called straight polarity. In DCEN, the electrode is connected to the negative terminal and the work is connected to the positive. The other way to connect DC is DCEP, which is DC electrode positive, often called reverse polarity. Many stick welding electrodes operate on DCEP. but some are designed to work with DCEN or AC, so check the manufacturer's recommendations for the proper settings. Stick electrodes are made with a variety of metal alloy compositions and flux chemistries. You'll want to make sure the electrode you plan to use will be strong enough and that it's compatible with the base metal and the position of the joint you want to weld. Often, electrodes have the American Welding Society classification code printed on them. This code will identify tensile strength, the flux covering type, the appropriate welding positions, and sometimes other important information. So, in summary, stick welding is an electric arc welding process. It uses a consumable electrode rod that is covered with a flux material. When heated, the flux releases shielding gases that protect the weld. A layer of slag covers the weld while it solidifies and is removed when the metal cools. Stick electrodes are not all the same and must be chosen for the specific job they need to do.
Gas metal arc welding. Gas metal arc welding was formerly called metal inert gas welding. It is an improvement over stick welding because an uncoated wire electrode is fed into and through the torch, and an inert gas, such as argon, helium, or carbon dioxide, flows out around the wire to protect the puddle from oxygen. This method of welding can be used for large volume manufacturing and production work. It is not well suited to repair work because weld quality cannot be easily determined without destructive testing. The power supply is connected to the torch and the work, and the arc produces the intense heat needed to melt the work and the electrode. Low voltage high current DC is typically used with gas metal arc welding. Figure 5-5 shows the equipment required for a typical metal inert gas welding setup. A short video of gas metal arc welding that will help you easily understand.
What is MIG welding? MIG stands for Metal Inert Gas Welding. The American Welding Society calls this process gas metal arc welding, or GMAW. You might also hear it called wire welding. In MIG welding, a thin wire acts as the electrode. This wire is fed from a spool mounted on a gun or inside the welding machine through a flexible tube and out of the nozzle on the welding gun or torch. The wire is fed continuously when the trigger on the welding gun is pulled. When this trigger is pulled, it also switches on the welding current and a shielding gas. An electric arc forms between this wire electrode and the workpiece and heats both metals above their melting point. These metals mix together or coalesce and solidify to join the workpieces into a single piece. The metal in these parts to be joined is called the base metal, and the metal that comes from the melting wire electrode is called filler metal. MIG welding always adds filler metal to the joint. Because the wire electrode melts as it's being used, MIG is called a consumable electrode process. Here's the MIG wire going through the wire feeder into a flexible tube or conduit liner. The liner goes through the hose or welding lead all the way to the torch nozzle. At the nozzle, the wire is fed through a contact tip and comes out at the point of the weld. Shielding gas is also fed through the welding lead. It goes through a gas diffuser and flows out of the nozzle. This shielding gas, which is often a mix of argon and CO2, protects the molten metal from reacting with oxygen, water vapor, and other things in the atmosphere. The shielding gas is stored in high-pressure cylinders like these. The pressure is reduced to a usable level by a device called a regulator. In MIG welding, all the machine controls are set on the machine itself. The most important of these are polarity, wire speed, and voltage. The trigger on the gun is just an on-off switch. For most MIG welding, the current is direct current, or DC. DC is like the current flowing from a car battery. One wire is always the negative, and one is always positive. In DC MIG welding, the electrode is usually positive and the workpiece is negative. The term DCEP is used, indicating that the current is direct current and the electrode is positive. This is also called reverse polarity, but DCEP is a more descriptive term. In an electric circuit, the current flows in a loop. In MIG welding, the current has to flow in a complete circle from the machine to the torch, into the work, and back to the machine. A work lead is clamped to the work to complete the circuit from the workpiece back to the machine. So, in summary, MIG welding is an electric arc welding process. It uses a consumable wire electrode. Filler metal is added automatically, and the shielding gas comes from a high-pressure cylinder.
Gas tungsten arc welding. Gas tungsten arc welding is a method of electric arc welding that fills most of the needs in aircraft maintenance and repair when proper procedures and materials are used. It is the preferred method to use on stainless steel, magnesium, and most forms of thick aluminum. It is more commonly known as tungsten inert gas welding and by the trade names of heliarc or heli-weld. These names were derived from the inert helium gas that was originally used. In tungsten inert gas welding, the electrode is a tungsten rod that forms the path for the high amperage arc between it, and the work to melt the metal at over 5,400 degrees Fahrenheit. The electrode is not consumed and used as filler, so a filler rod is manually fed into the molten puddle in almost the same manner as when using an oxyacetylene torch. A stream of inert gas, such as argon or helium, flows out around the electrode and envelops the arc, thereby preventing the formation of oxides in the molten puddle. See Figure 5-7. The versatility of a tungsten inert gas welder is increased by the choice of the power supply being used. Direct current of either polarity or alternating current may be used, shown in Figure 5-8. Here's a short video of gas tungsten arc welding.
What is TIG welding? TIG stands for tungsten inert gas welding. The American Welding Society calls this process gas tungsten arc welding, or GTAW. You might also hear it called heliarc welding. TIG welding uses a tungsten electrode, and tungsten has an extremely high melting point. When you TIG weld, the electrode gets hot, but it doesn't melt. We say that it's a non-consumable electrode. That doesn't mean it lasts forever, that just means that it doesn't melt and become part of the weld. You see, in a lot of other welding processes, the electrode melts and becomes filler metal. Those are consumable electrode processes. So here's the tungsten electrode being held in a TIG torch. The electrode slips into a collet, and the collet tightens up against the collet body. You can adjust the length that the electrode sticks out of the holder by loosening up the end cap. When you tighten the end cap, the collet clamps down on the electrode. TIG works by melting the base metal, and that is the metal that makes up the two pieces that are to be joined. The heat is generated by an electric arc that forms between the base metal and the tungsten electrode. You can control the amount of heat with a foot pedal or with a thumb wheel on the torch. For most metals, the current is direct current, or DC. DC is like the current flowing from a car battery. One wire is always the negative and one is always the positive. In DC TIG welding, the electrode is usually negative and the workpiece is positive. The term DCEN is used for this, indicating that the current is DC and the electrode is negative. This is also called straight polarity, but DCEN is a more descriptive term. DCEN puts most of the heat on the workpiece, and it's the most common setup. When welding aluminum, however, AC is used. In AC, the positive and negative voltages switch back and forth between the electrode and the workpiece. This puts more heat on the electrode, but it has a cleaning effect on the workpiece. You see, aluminum forms oxides that float to the top of the weld pool and prevent a good weld. AC current helps control these oxides. In an electric circuit, the current flows in a loop. In TIG welding, the current has to flow in a complete circle from the machine to the torch, into the work, and back to the machine. A work lead is clamped to the work to complete the circuit from the workpiece back to the machine. Now, you can TIG weld with or without filler metal, and that's not a choice you have in a lot of other processes. If you want to add filler metal to a TIG weld, use a filler rod, which is just a rod of metal with a specific alloy. You want to make sure that the filler metal you're using is compatible with the base metal and that it has the strength required to do the job. In TIG welding, the molten metal is protected by a shielding gas. This gas, usually argon and sometimes helium or other gases, keeps the molten metal from reacting with oxygen and water vapor in the atmosphere. This shielding gas is stored in high-pressure cylinders like these. The pressure is reduced to a usable level by a device called a regulator. The shielding gas flows through a hose and comes out right at the point of the weld. So in summary, TIG welding is an electric arc welding process, uses a non-consumable tungsten electrode, the filler metal is added separately in the form of filler rod, and the shielding gas comes from a high-pressure cylinder.
Plasma arc welding. Plasma arc welding was developed in 1964 as a method of bringing better control to the arc welding process. Plasma arc welding provides an advanced level of control and accuracy using automated equipment to produce high-quality welds in miniature and precision applications. Furthermore, plasma arc welding is equally suited to manual operation and can be performed by a person using skills similar to those for gas tungsten arc welding. Plasma gas is normally argon. The torch also uses a secondary gas, such as argon helium, argon nitrogen, or argon hydrogen, that assists in shielding the molten weld puddle and minimizing oxidation of the weld. Like gas tungsten arc welding, the plasma arc welding process can be used to weld most commercial metals, and it can be used for a wide variety of metal thicknesses. When plasma arc welding is performed manually, the process requires a high degree of welding skills similar to that required for gas tungsten arc welding. However, the equipment is more complex and requires a high degree of knowledge to set up and use. The equipment required for plasma arc welding includes a welding machine, a special plasma arc control system, the plasma welding torch, water-cooled, the source of plasma and shielding gas, and filler material, when required. Because of the cost associated with this equipment, this process is very limited outside of manufacturing facilities. In the plasma welding torch, a non-consumable tungsten electrode is located within a fine-bore copper nozzle. A pilot arc is initiated between the torch electrode and nozzle tip. This arc is then transferred to the metal being welded, shown in Figure 5-11. Figure 5-12 shows, by forcing the plasma gas and arc through a constricted orifice, the torch delivers a high concentration of heat to a small area. The plasma process produces exceptionally high-quality welds. More information about the plasma arc welding in this next short video.
In plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch plenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application.
Plasma arc cutting. When a plasma cutting torch is used, the gas is usually compressed air. The plasma cutting machine works by constricting an electrical arc in a nozzle and forcing the ionized gas through it. This heats the gas that melts the metal, which is blown away by the air pressure. By increasing air pressure and intensifying the arc with higher voltages, the cutter is capable of blasting through thicker metals and blowing away the dross with minimal cleanup. Plasma arc systems can cut all electrically conductive metals, including aluminum and stainless steel. These two metals cannot be cut by oxy-fuel cutting systems because they have an oxide layer that prevents oxidation from occurring. Check this video for more info about plasma arc cutting.
If you're in the metalworking business, you've heard about plasma cutting systems. Plasma's combination of cut quality, productivity, and versatility make it one of today's most popular industrial cutting processes. But first, what is plasma? Plasma is often called the fourth state of matter. Let's take a look at the three other states we're all familiar with. They are solid, liquid, and gas. The difference between these states is their energy. When you add energy to ice in the form of heat, the ice melts and forms water. If you add more energy, the water vaporizes and becomes steam. From ice to water to steam. But what happens if you add even more energy to the steam? A lot more. If you could heat it to 11,700 degrees Celsius, the steam would break up into a number of component gases. It would also become electrically conductive or ionized. This high-energy ionized gas is called plasma. Plasma is created when you expose a gas to very high temperatures or when you pass electricity through it. Our most familiar form of plasma is probably the gas inside a fluorescent or neon light bulb. Lightning is an example of plasma on a larger scale. And on a very much larger scale, our sun and all the stars are also made of plasma. Plasma is quite remarkable. It has no specific shape. It's also a bit like a metal in that it easily conducts electricity and produces and responds to magnetic fields. Because of these unique properties, plasma can be tremendously useful, which brings us back to metal cutting. Now that we have a better idea of what plasma is, let's see how it works. Here's the inside of a plasma torch, the kind typically used on cutting tables. Compressed air, nitrogen, or other gases provide a source for the plasma. In this example, a second inert shield gas is used to protect the workpiece and blow off melted metal. The electricity supplies the energy needed to turn the gas into plasma. The greater the current, the hotter the plasma. A specially engineered nozzle and electrode constrict and maintain the plasma jet, concentrating it into a small area so it can be used for cutting. When the operator is ready to cut, a start signal is sent to the DC power supply. A circuit temporarily connects the nozzle to the positive side of the power supply with the electrode at negative. Next, a high-frequency spark ionizes the gas and makes it electrically conductive. This creates a current path between the electrode and the nozzle and forms a pilot arc of plasma. The workpiece is connected to a ground through the cutting table. When the pilot arc contacts it, the plasma arcs transfers to the workpiece, melting the metal. The high-velocity gas blows the molten material away. And that brings us to the end of our brief journey into the fourth state of matter.
Electric resistance welding. Typically used to join thin sheet metal components during the manufacturing process. Spot welding or resistance spot welding used to weld various sheet metal products, through a process in which contacting metal surface points are joined by the heat obtained from resistance to electric current. Seam welding is the process of joining two similar or dissimilar materials at the seam by the use of electric current and pressure. The process is mostly used on metals since they conduct electricity easily and can sustain relatively high pressures. Seam welding is same as of spot welding. Difference is that in case of seam welding the rotating wheel is used and it is the fast process than spot welding. A short video on how spot and seam welding works.
A resistance spot welder is designed to deliver a low-voltage, high-current electrical pulse. The weld electrodes are made of copper because copper has a low resistance to current flow, which allows it to conduct electricity with ease. Steel is a very poor conductor of electricity, and it will resist the weld current as it flows from the spot welder. The friction created by the current forcing its way through the metal heats the weld area to over 2,000 degrees Fahrenheit. The squeeze pressure from the weld electrodes now compresses the molten area and fuses the two metal surfaces into one solid nugget. By maintaining the squeeze pressure for a short time after the weld current is shut off, which is known as hold time, The molecules in the welded material remain compressed as the weld cools. This additional pressure results in a much stronger weld.